Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and in this video, I'm going to be working through a medium complex example of AC circuit analysis by first finding the transfer function and then plugging in for omega. Let's look at another example. Here's a circuit where I have defined V out to be the voltage across the capacitor. Now that is not what we usually see, but it's perfectly valid. So let's figure out how we're going to analyze this circuit. We could use mesh analysis or nodal analysis. I'm going to go ahead and use nodal analysis. I don't know that it matters which one. This voltage here is the input voltage Vn. This voltage here, I will give a name. I'm going to call it V1. And we want to note that our output voltage, which is what we care about, is going to be equal to Vn minus V1. Okay, so what I want to do is ultimately I want to do this analysis using passive filtering techniques. So I'm going to first find V out over Vn. Okay, and so that's the transfer function. But what I need to solve for is really Vn and V1 so that I can manipulate Vn and V1 to get V out, and thus the ratio there. So let's go ahead and write some equations. At this equation, at this node Vn, we just write, it is Vn. So let's write an equation here at V1, see what that gets us. Okay, so we'll have V1 minus Vn. Let me show you what we're doing. V1 minus Vn over 1 over Sc. And then we have V1 minus 0 over R2 plus V1 over SL equal to 0. And so that's the equation we're going to work with. Let me go ahead and pull that to the next page, and we're going to just do some algebra. And however you choose to solve for this is fine, but remember what we're trying to get is V out over Vn. So the way I'm going to work this problem is I'm going to first pull V1 out of the left-hand side and move Vn to the right-hand side. So I'll have V1 times 1 over Sc plus 1 over R2 plus 1 over SL will be equal to Vn over 1 over Sc. Okay. If we go ahead and flip our fractions there, we'll end up with V1 times Sc plus 1 over R2 plus 1 over SL will be equal to Vn times Sc. And at this point, what I'm going to do is I'm going to solve for V1 over Vn. Like I said, there's other choices of how to get where you're going, but this is what I'm going to do. V1 over Vn will be equal to Sc over Sc plus 1 over R2 plus 1 over SL. To go ahead and get this in a slightly nicer form, I'm going to multiply by SLR2 over SLR2. That'll clear the fractions in the denominator, and I definitely like to go ahead and clear those fractions. And what I'll end up with is S squared LCR2 over S squared CLR2 plus SL plus R2. Okay, so that gives us this gives us a value, a transfer function, not the one we're looking for, but it is a transfer function. And then we remember, of course, that V out is equal to Vn minus V1. So V out over Vn will be equal to 1 minus V1 over Vn, which is what I solved for. So now I can write V out over Vn will be equal to a rather messy thing. So I'm going to have the denominator be S squared CLR2 plus SL plus R2. And then I'll have S squared LCR2. And then let's go ahead and do the 1 will be S squared LCR2 plus SL plus R2, right? That over the denominator is 1. And then V1 would be S squared LCR2 over the same denominator. So that gives us V out over Vn will be equal to SL plus R2 over the denominator S squared CLR2 plus SL plus R2. And there's our expression for V out over Vn. So we have kind of a lot of messiness going on, but that's okay. Now that we have written the transfer function V out over Vn, we can plug in values corresponding to our circuit elements. Remember we had R2, let's see, L is equal to 150 millihenries. So we'll have S times 0.15, which is millihenries, plus R2 is 200 over S squared C, which is 1 millihenry. Let's see. So 1 millihenry is 0.001 millifarad. 1 millifarad is 0.001. L is 0.15. R2 is 200 plus S times 0.15 and then plus 200. Okay, so there's all my values just plugged in. When I simplify that, what I get is 0. I'm not sure I wrote that down. Okay, so at this, I didn't write down that intermediate value. So what we're going to do is we're going to go ahead and we're going to plug in S is equal to J omega, and omega was 1,000 for my input. So when I plug that in, what I'm going to end up with is 150. Oh, let me rephrase that. Let's write it as real plus imaginary. So I'll get 200 plus 150J. And then the denominator simplifies to minus 29800 plus J times 1.50. Yep. And when we solve that, we end up with minus 0.0067 minus J 0.0051. So this gives us H of J1000 will be equal to that. The next step is to do our multiplication. So just to give you an intermediate value here, if we want to go ahead and convert this to polar form, we plug in the numbers, do the conversion, and we end up with 0.00839 at an angle of sorry, I'm reading, double check my answers, minus 142.8417 degrees. Okay, so if we take that, now we want to solve for V out. V out will be equal to H times V in. So we have H, which is 0.00839 at an angle of minus 142.8417 degrees. And then Vn, of course, let's see, what was Vn? Vn was 10 cosine of 1000 t plus 30 degrees. So that's 10 at an angle of 30. So when we do that multiplication, it's easy when it's in this form. We end up with V out magnitude is 0.839 and an angle of minus 112.8417 degrees. So there it is in polar form. If we want to write that as a time-varying signal, which I encourage you always to do, you'll end up with 0.0839. Cosine omega, and omega was 1000, so 1000 t minus 112.8417 degrees volts. And there's our answer. Thanks for watching. I hope you found this video useful.